Hi there, you are watching a video of API 653 inspection and repair of above ground storage tanks. Let's start with section 4, suitability for service. When an inspection shows that a change has occurred from the original physical condition of the tank, an evaluation should be made to determine its suitability or reliability to continue in service. This section of the API 653 standard provides a suitability for service assessment for existing tanks, or for a change of service, or when making decisions involve repair, alteration, dismantling, relocation, or reconstruction of tanks. The following lists some of the more common situations that may require a suitability for service evaluation, but it is not intended to replace a detailed engineering analysis or the judgment required for any situation. For example, internal corrosion, external corrosion, properties of the stored product, minimum design metal temperature, leaf loads on the roof, wind and seismic loads, tank foundation, mechanical properties of construction materials, operating conditions, etc. Let's look with more detail the suitability for service of the different components of the tank. Let's start with the suitability for service of the roof. The structural integrity of the roof and roof supports must be evaluated. Sheets that have corroded to an average thickness or less than 2.3 mm or any holes must be repaired or replaced. Fixed roofs. Roof supports elements, beams, columns, and rafters must be inspected by a method acceptable to the responsible inspector. Items that are distorted, such as out-of-plumbness columns, corroded or damaged, will be evaluated and repaired or replaced if necessary. Special attention must be paid to the possibility of severe internal corrosion of pipe columns, as corrosion might not be evident by external visual inspection. Regarding floating roofs, those areas of the plates and pontoons that show cracks or perforations must be repaired or replaced. Likewise, holes through the roof sheets will be repaired or replaced. Also, pitted areas should be evaluated for the possibility of holes developing prior to the next scheduled internal inspection. If so, the affected areas will be repaired or the plates replaced. When it comes to change of service, when the working conditions of a tank change, pressures and temperatures should be evaluated for the new service as well as to verify that the overall design meets the current design standard. These evaluations include internal pressure, external pressure, operation at elevated temperature, when the new operating temperature is greater than 93 degrees Celsius, must be verified according to API 650 Annex M. Operation at a temperature lower than the original design temperature. Venting. The effects of a change in operating conditions on normal and emergency venting requirements must be met. Now let's talk about the suitability for service of the shell. Tank shell evaluation. Flaws, deterioration, or other conditions, for example, change in service, relocation, corrosion greater than the original corrosion tolerance, etc., that may adversely affect the performance or structural integrity of an existing tank should be evaluated to determine if it is fit for the intended service. These flaws will be detected and evaluated as per the different inspection methods stated in the standard. Let's talk about the actual thickness determination. Section 432. To determine the actual thickness where there are considerable corroded areas, the API 653 in section 4321 indicates the controlling thicknesses will be determined according to the following procedure. Figure 4.1. First, for each area, the authorized inspector will determine the minimum thickness, T2, at any point in the corroded area. Second, the critical length, L, should be calculated as follows. L is 3.7 square root of D and T2, where L is the maximum length in the vertical plane. This distance will not be more than 40 inches, 1016 millimeters. D is the diameter of the tank in feet. T2 is the minimum thickness in the selected corroded area, excluding pitting. The third step. The authorized inspector shall decide, visually or otherwise, which vertical plane in the area, or planes of course, are the most likely to be affected by corrosion. The thickness measurements will be averaged from at least 5 equally spaced measurements along each vertical plane for the distance L to determine the lowest average thickness, T average or T1. Step 4. Criteria for the continued operations of the tank shell are the following. First one, T1 must be larger or equal as T minimum, subject to verification of all other loads listed in API 653, section 4335, where T minimum is the minimum thickness of the tank shell. Second verification criteria. T2 must be larger or equal of the 60% of T minimum, and third, any corrosion tolerance required for service until the next inspection must be added to T minimum and 60% of T minimum, where T minimum is the minimum acceptable shell thickness that will be calculated later on. Isolated pitting in the tank shell can be ignored as long as the following requirements are met. No pit depth results in the remaining thickness being less than half the minimum acceptable thickness, exclusive of the corrosion tolerance, and the sum of its dimensions along any vertical line does not exceed 50 mm in a length of 200 mm, as shown in the figure to the right. Let's review the minimum tank shell thickness calculation. In general, calculating the minimum acceptable thickness for a complete shell course is carried out according to section 4331A, using the liquid height of the stored product, H, to the bottom of that particular shell course. If there are locally thin areas or specific areas need to be investigated, such as locations where nozzles are required, the method given in 4331B can be applied using the liquid level H for that particular location. Let's see this in a little bit more detail. The minimum acceptable thickness of shell plate for continued service shall be determined by one or more of the methods indicated below. These methods are limited to tanks with diameters less or equal than 61 meters. When determining the minimum acceptable thickness for an entire shell course, the minimum thickness is calculated as follows. Whereas, when determining the minimum acceptable thickness for any other part of the shell course, such as a locally thin area or any other location of interest, the minimum thickness is calculated as follows. Let's discuss all these variables in detail for both of the equations mentioned before. On the right, we can see both equations for the entire shell course or for a thin area. T minimum is the minimum of acceptable thickness in inches, not less than 0.1 inches or 2.5 millimeters. D is the nominal tank diameter in feet. H is the height from the bottom of the shell course being evaluated to the maximum design liquid level when evaluating a complete shell course in feet, or it could be the height from the bottom of the length L at the thin area or any other area of interest to the maximum liquid design level in feet. G is the highest specific gravity of tank contents. E is the original joint efficiency for the tank. If the original efficiency is an unknown, the API 653 table 4.2 must be used. S is the maximum allowable stress in PSI, and the maximum allowable stress is obtained through Y, the variable Y, that is the specified minimum yield strength, and T, that is the minimum tensile strength. For one of the API 653 standard, shown on the screen, presents all the materials that can be used for the repair or construction of storage tanks. So in this table we will find the values of the allowable stress, yield strength, and minimum tensile stress. Table 4.2 shows the joint efficiency values to be used in case that the value is unknown for a particular tank. Regarding the minimum tank shell thickness calculation, and alternatively to the methods indicated before, the shell thickness for tanks with diameters up to and including 61 meters can be calculated according to the API 615 standard using the variable point design method. As an alternative to the procedures described, any tank shell thickness reduction below the required minimum can be evaluated using the design by analysis method defined in the ASME Code Section 8 Division 2 Appendix 4 or in the API 579 Standard Section 5, 4 and 6. Let's discuss about distortions. Out of roundness, buckling, flattened areas, dents, or some other distortions like picking or banding at the joints can be caused by a lack of pressure, excessive pressure, improper fabrication, or inadequate repairs. These distortions must be evaluated to determine the appropriate corrective actions. If the tank continues to operate with these distortions, depending on their magnitude, it may collapse. Regarding flaws, such as cracks and laminations, these must be examined and evaluated to determine their nature and extent. If a repair is required, a repair procedure should be developed and implemented. Shell welds. The condition of the tank shell welds must be evaluated for suitability for service. If necessary, a repair procedure must be established, or the safe operating height must be adjusted. Some typical discontinuities in welding and repair procedures are given in point 97 of the API 653 standard. All existing tank shell penetrations must be reviewed and evaluated, and the appropriate repairs made while maintaining the integrity of the tank shell. The type and size of reinforcement, weld spacing, and the thickness of reinforcement plates, nozzle necks, flanges, etc. should also be checked and repaired as necessary. Suitability for service of the tank bottom. In general terms, tank bottom inspections, when used in conjunction with the procedures in this standard, should provide sufficient data to ensure that the integrity of the tank bottom will prevent leakage that may cause environmental damage. All aspects related to corrosion phenomena and other possible leakage or damage mechanisms must be examined. A periodic evaluation of the integrity of the tank bottom will be carried out in addition to the internal inspections specified in API 653, section 6.4. Foundation settlement can affect the integrity of the shell and bottom, and monitoring tank settlement is a recognized practice to assess integrity. Tank settlement evaluation techniques are listed in API 653 Annex B. Causes of tank bottom failure. The following list presents some historical causes of bottom leaks or failures that should be considered when lining, repairing, or replacing a tank bottom. For example, internal pitting, corrosion of welds, stresses induced in the bottom, corrosion on the underside, inadequate drainage, lack of annular plates, irregular settlement, insufficiently filled voids, inadequately supported sumps. On the left picture we can see a very corroded weld, and likewise on the right picture we can see very corroded bottom plates. Release Prevention Systems, RPS. This term refers to the set of standards and recommended practices that are designed to maintain tank integrity and thus protect the environment. According to the API 653, section 443, with respect to tank bottoms, these measures include internal inspection of the tank bottom, installing cathodic protection for the underside of the tank bottom, coating the inside of the tank bottom, installing a barrier under the tank bottom. The picture shows a barrier or lining under the tank bottom and on top of the concrete foundation. Tank bottom plate thickness measurements. There are several methods available to determine the external, solid side, corrosion of the bottom plate. Methods vary in the extent to which they can reliably measure general corrosion and pitting. A combination of these methods, together with extrapolation and analysis techniques, may be required to establish the likely conditions of the entire tank bottom. Magnetic flux leakage (MFL) tools are commonly used in conjunction with ultrasonic thickness (UT) tools to examine tank bottoms. Ultrasonic thickness measurement techniques are often used to confirm and quantify data obtained by magnetic flux leakage examination, although these techniques may not be necessary. API 653 Annex G can be used to provide guidance to qualify personnel and procedures for obtaining thickness data. The minimum acceptable remaining thickness of the bottom of a tank can be calculated according to the API 653 section 4451 as indicated below. The equation is explained with the following terms. MRT is the minimum remaining thickness at the end of the interval OR. The interval OR is the years of in-service operations until the next interval inspection. RTBC is the minimum remaining thickness due to the soil side corrosion after repairs. RTIP is the minimum remaining thickness due to corrosion on the product side, after repairs as well. STPR is the maximum unrepaired corrosion rate on the product side, and UPR is the maximum corrosion rate on the soil side. This equation for the minimum remaining thickness could also be rearranged, obtaining the maximum inspection interval OR as displayed on the screen. Table 4.4 indicates the minimum bottom plate thickness at the next inspection interval, depending on the tank bottom and foundation design. Unless a stress analysis is carried out, the minimum thickness of the plate in the critical zone of the tank bottom will be the lesser of the following: half the original thickness of the bottom, not including the original corrosion allowance, or 50% of T minimum of the lower shell cores according to paragraph 4331, but never less than 2.5 mm. Repairing internal pitting, when carried out to extend the period of operation in service, should either be by pit welding, weld overlay, or a lap weld patch, followed by the appropriate inspection and testing requirements. Let's talk about tank bottom plate thickness measurements. According to section 446 of the API 653 standard, due to strength requirements, the minimum thickness for an annular plate it is usually greater than 2.5 mm. Isolated pitting caused by corrosion does not appreciably affect the strength of the plate. As for the minimum thickness of annular plates, unless a stress analysis is performed The thickness of the bottom ring plate shall be in accordance with the following. 1. For products with specific gravity less than 1 that require annular plate other than for seismic loads, the thickness shall be as per API 653, table 4.5 plus corrosion allowance. 2. For products with specific gravity larger or equal than 1 that require annular plate other than for seismic loads, the thickness shall be as per API 650, table 5.1a plus corrosion allowance. 3. For tanks that use thicker annular plates for seismic considerations, a seismic evaluation should be made in accordance with the original construction standard. And 4. The criteria in API 653 section 4457 will be used to determine the thickness and the projection of the annular plate beyond the edge. As indicated before, the minimum thickness of annular plates can be established by means of using table 4.5 of the API 653 displayed on the left of the screen, or table 5.1a of the API 650 standard, shown on the right part of the slide. Let's now review Annex B, Foundation Settlement. When determining the effects of soil settlement in storage tanks, it is a common practice to monitor bottom settlement to determine the effects of the soil on the settlement of storage tanks. In most cases, this monitoring program begins during construction and continues through hydrostatic testing and subsequent operations. During operations, the frequency of settlement measurements should be based on the soil settlement predictions. If at any time the settlement of a tank is considered excessive, the storage tank must be emptied and apply a procedure to re-level the tank. Re-leveling a tank is difficult to achieve and expensive. Therefore, proper interpretation and evaluation of the settlement data is critical when assessing whether or not to re-level a tank. Approaches used to remediate shell and bottom settlement include localized repairs of the bottom plates, partial re-leveling of the tank periphery, and major re-leveling of the entire tank bottom. Complete re-leveling of the tank, which involves raising the shell and bottom fully at the same time, can introduce highly localized stresses to the structure and impair its integrity. Alternatives other than a full tank lift should be considered as the first choice. Let's review now the types of settlement. The types of settlement that can occur in a tank are primarily associated with the tank shell and the bottom plates. Uniform settlement. This type of settlement can often be reasonably predicted from the soil tests and will vary in magnitude depending on the soil characteristics. Uniform settlement in a tank does not induce stress on the tank structure, but it does on the connections attached to it. Flat slope, rigid body tilting. This type of settlement tilts the tank on an inclined plane. The inclination can cause an increase in the liquid level and therefore an increase in the stress levels in the shell and its welded joint. Also, excessive inclination can cause the perimeter seals in a floating roof to bend and restrict its movement. Differential settlement out of plane. Due to the fact that the tank is a flexible structure, it is likely that the tank will settle in a non-planar configuration, which induces additional stresses in the shell. The differential settlement is the most important component to determine and evaluate to ensure tank shell and bottom integrity. Edge settlement. Edge settlement occurs at the periphery of the tank bottom, resulting in deformation of the bottom plate near the shell to bottom junction. Bottom settlement. Depressions and bulges can occur in a random fashion, depending mainly on the construction method. The appearance of this type of settlement is mainly a result of localized stresses in the bottom plate. The question at this point is the following: what is the acceptable settlement in a storage tank? So, the determination of an acceptable settlement is carried out according to what is stated in Annex B. When the limits of acceptable settlement are exceeded, the repair of the areas involved should be considered, or an extensive stress analysis should be carried out, taking into account the knowledge of the following: tank service history, previous repairs, previous inspections, conditions of the tank foundation, soil characteristics, construction material, and estimates of future settlements.